Hello, welcome to part 5 of our course on analog space missions. Today we're going to talk about experiments, how you select them and what kind of experiments you have in analog bases. Just a note before we get started, last time we were discussing habitats, and since I made a video for habitats, actually there was a volcanic explosion on the island where the High Seas Analog Space Mission Station is actually located. So far we're quite happy, it hasn't gotten damaged, but what's quite interesting is we were discussing last time about location, about extreme environment, about some of the dangers involved and just logistics. See, when you are on an active volcano, this is the kind of thing that you can see happening, and the monitoring, the understanding and the whole danger thing really does add an extra dimension. So when you're thinking about installing your base, do keep that in mind that, building next to an active volcano might come with some complication, although it also comes with a bit of a, added danger in simulation. At the moment, High Seas is not being used, but still, it's quite an interesting addition. Anyway, let's get started. So, today, will be quite a short one normally, just experiments in analog space missions. So we discuss shortly why are we having experiments in analog missions, why not just, chill on the couch the whole time? What are kind of experiments that you can actually do, and how would you select them? Do you just take any random experiments, or do you just actually go through a massive process of selection? Then how do you train the analog astronauts? The analog astronauts are the ones who perform those experiments inside the base. It's quite unlikely they'd be able to do it without any sort of protocol or any form of training, so you need to go through this with them. Then the logistics involved, and then how you publish results. So it's quite often that you would publish results out of the experiments that you would do in analog missions, even if it's only 2 weeks a week. And yeah, so we just go over all of this today. So why experiments? Here you got a little example of an experiment by Astroland. You can have a look into their webpage. They are focused mostly on geology and exobiology. It's quite interesting. Astroland used to be, so they have a huge cave, about 1.5k long, with 2 underground lakes. And the cave is not completely sealed, but they used to be underwater. And because of this, they're kind of plants and biology and kind of rocks you find in there are actually quite different from what you would find on the surface, and it makes it very, very interesting because it really makes it much more like the way you would explore if you were on other planetary body. You can find some things that you've never seen before on Earth, not see something completely alien, but it does make the biology and the research itself quite interesting. So do have a look at the publications that they have and the research they have ongoing. It's quite interesting, and it's a lovely cave. But yeah, so why experiments? Well, when you send astronauts to the International Space Station, at the moment you do a lot of experiments. It's worth the trip. A lot of things can be actually tested in space. The way the microgravity affects bodies, not only just so we can live there, but just in general to understand biology. How does that actually influence our bodies? The fact that we have gravity on Earth. The other thing is radiation, for example. So these are the things that you test in space. Obviously, in analog missions, you don't have microgravity, and usually you're quite shielded from radiation. However, you can train the astronauts, the analog astronauts, to become real astronauts. If you were to not give them any experiments, they would be locked in a tin can or inflatable habitat or whatever it is for a long period of time with nothing much to do. By giving them experiments, you actually, in a way, keep them busy, you keep them trained, you teach them how to perform the way a real astronaut will actually perform. So that's already the kind of thing of making it more realistic compared to the job of a real astronaut. The other thing is extremely interesting. Most of the people in those analog space missions are actually very interested in science, and there's a lot of factors that you can actually test, mostly psychological. What happens when you're in isolation? What happens when you're in a small group? What happens when you have a tight schedule? From a psychological and physiological standpoint, a lot is happening, and then you can test that for habitats. We mentioned last time, for example, you could do a psychology study on the effects of habitat colors, habitat sound, and habitat structure. What does it impact, or how does it impact you if you were to have only one table in the middle of the kitchen, for example, instead of having the table in a less social environment? There's a lot of parameters that you can test, and then you can transcribe this completely or partially to further space settlements or the ISS, etc. So there's already this that's quite interesting. And the other thing is that you can get in environments that are quite extreme, that you might not always have the opportunity to do some research, and that you would actually take the time because you need the astronauts to be busy and you're in this extreme environment, and then you can coincide the two. So it's quite interesting, the things that you can do in our space missions. And also when you think about when we would go to the Moon and Mars, we have a lot of research to be done. We have to, look at the field. For example, is it going to be a stable structure? We're going to be able to build a habitat easily, or do we need to, build an underground structure to make sure we're going to be stable? So you need to do geophysical studies. Then you have to do biology studies. Is there any life on Moon and Mars? So far we haven't found any, but that's still science that you have to do. Then is the whole finding the right materials. So for example, going and extracting materials so that we could have rocket fuel for the way back, or we want to 3D print our houses. Again, you need to do some experiments. So even if we were to send astronauts to Mars and say, well, they have time to chill and watch a movie, they don't need anymore to have a tight schedule, it is still likely that you would have a lot of science to do. You would have a lot of experiments to do. There's a lot that we still don't know. So it makes sense to do those experiments. What is very interesting is when you do the experiments in an Analogue space mission, you are not in the lab environment. You can recreate partially a lab. We did discuss this in the habitat. You could have a clean room if you have the money. But in general, you don't have the same kind of controlled environment. You don't have the same requirements as you have in a normal lab. And that can actually impact your experiments. It can actually change the quality of your work. So yeah, it's quite interesting, the wide aspect array, and we can talk about that. So medical, and by this I mean physiology and psychology. So medical, why do you do medical tests? Well, there's the whole training aspect. Obviously, when you're in the International Space Station, you take a lot of blood samples, urine samples, hair samples, whatever it is. Almost everything about your body is being measured. Okay, you are real life lab rat, basically. And it's actually quite interesting. When you give your body to become an astronaut, you give everything. It's your mind, it's your time, it's your energy, and it's your physiological parameters. Why? Well, obviously we need to understand the gradation of the body, and you can think, well, there's no radiation, there's no microgravity in Analogue space missions. True, but there's other factors. For example, in one of the missions the temperature was 13 degrees instead of 18 degrees, and then suddenly we were eating way more. And for example, if you were to take physiological parameters, you'd probably be able to see, well, actually that wouldn't be sustainable in a long time. A lot of people in the crew will be losing a lot of weight, and that's actually not going to work. It's quite simple, but it's something that you should be measuring. And you could probably measure simply the increase in metabolism rate and just energy consumption. You could measure the heart rate, also see is the astronaut stress. These are the parameters that you, for example, measure also doing an EVA. Like, do you see if the heart rate is going up? Does that mean that the astronaut is stressed? Are they focused enough? Is there a way we can adapt this? Usually the isolation has a psychological impact, but we also know that psychology has an impact on physiology. So if you were to stress a lot, possibly you could also impact your biological function, and then on the long term this could have consequences on either your well-being in general, but also the mission. So yeah, medical, obviously there's a lot of things we can do. You can do some other measurements, maybe about colors, about teamwork. So psychologically there's a lot that can be done in our space mission. One of the reasons why it's also a lot that can be done is simply because it's usually quite easy. Like, you just have a questionnaire to fill, you just have to fill in some documents. So the amount of logistics involved is much lighter than for experiments like with chemistry and biology and just medical, where you really need all the apparatus and it's way more expensive. So yeah, so psychology, it's quite good, it's quite interesting because you already change quickly from a normal situation, like being at home and seeing your family and seeing friends every day, to suddenly being in isolation, and not isolation like pro-COVID, but isolation for an analog mission. Then chemistry and biology, as we mentioned before, you can do some biological experiments, just like, you know, developing cells, but also from an agriculture standpoint, you can do aeroponics, hydroponics, really try to grow some food at home. One experiment that we discussed was the use of a robot that was Robot Hub, I think it was called, and it would basically check on plants, and it would see, okay, is that plant fit enough? Does it need more water? Does it need more light? And then you grow crops like this, and you test. The experiment is basically testing the robot's ability to maintain those crops. And that's actually quite important, because if you were to do long duration space flights, you would probably want to have some fresh vegetables, etc. And having a robot that can do this maintenance correctly is actually useful. It means you need less human beings to do it, and if one human is sick, then you know the plants might still be okay, or maybe the robot might actually be even better than a human at doing that. So that's an interesting factor, is thinking, well, you know, like we could test the robot itself and test how the plant is going, and then we can look at the crops. And what's quite nice too is that kind of application can also work on Earth. You can also check with a robot how your plant is doing and how it's going on. And another aspect of that experiment would actually be to collect human feces and, you know, kind of filter it slightly, feed it to the plants, and see, okay, are the plants growing that well, and basically see, is it a good fertilizer. Obviously it does work in general, but it would be good to see in a closed environment, would that work, and would the astronauts be too ill to actually eat from the same plant because they know what's been on them. Normally you just have to go with it, you know, just enjoy it. So yes, these are kind of experiments you can do. Chemistry, so there's chemistry experiments where, for example, you would measure the pH of a soil, you could measure like battery connectivity, whatever it is that you want to do. Basically, is there any proposition you think can be interesting, then can be done. Then engineering. By engineering, usually what we look at is, well, we talk about 3D printing, so sometimes, or like creating some parts. So that was done during one of the last Lunaris missions. In the Vulcan mission, they were 3D printed some parts that they needed for the rovers. Use of rovers is often a very strong point in analog missions that have EVAs, because those rovers help in guiding and telling, well, you could go left and right. This exploration is something that we will be using. We already use on the moon and Mars just for exploration and seeing, okay, is it worth going in that direction, that thing, what is there, do we need to bring sample back, do we need something to be carried by the rovers? I mean, it's easier for you not to be moving too much, but for the rover to carry things for you. So yeah, so that's a big part of engineering. Here on the right you can see a drone from the Austrian Space Forum that was used during MID-20, Aeroscan drone. So basically the goal was to use this drone to also, you know, map and evaluate some of the profiles. A bit more details if you look into it, but this is the kind of things that you would be testing in engineering. And the other part is obviously the base maintenance, so everything that has to do with, you know, sensors and life support systems, etc. That is obviously some engineering work to do. Then astronomy. Obviously it's a bit more complicated to do astronomy measurements when you are inside an analog base, but you can actually do some when you're doing EVAs, or if you have an opening, like if you're not on the ground, if you're on a dome, for example, and maybe you have a connection to a telescope, then you could be doing some astronomy measurements. So that's actually quite nice. It's not the main aspects of analog missions, because usually there's nothing, like you don't have huge telescopes, so you're not producing very, very high quality measurements. But still, it's quite interesting because it adds a bit this kind of magical and space-related dimension to the experiment. And obviously geology, yeah. So we mentioned before, it's very, very important, geology, because obviously understanding the soil is what's going to affect your habitats, but also your EVAs. Why? Basically, if your soil has very, very fine sand and toxic sand or any sharp elements, you won't be able to wear any normal spacesuits. You're gonna have to have a special spacesuit. You're gonna have to be very careful when you come in for the contamination. If you want to extract some of the soil to build or 3D print your habitat or any pieces, as we mentioned before, or if you want just to make fuel, or any basically component, any elements that you might want from the soil, you need to perform a geological measurement and say, well, this is what we need. One experiment that I did was called Red Moss, and we had to filter out what we call the perchlorate from soil. It was simulated Martian soil, and you have to remove the perchlorate, and you measure the pH, and at some point you should be getting to pH that is good enough for agriculture to be performed in this kind of soil. At the moment, if you were to take Martian soil, it's not good enough to grow plants. It's just not the right pH. But if you were to wash it, perhaps you could use it for that. But for this, you need to extract the soil, you need to be able to perform an analysis on it, you need to be able to understand what's going on. So geology is a very important field, and what's quite good is also it's not too complicated to do. You don't need to be in a very, very remote region to do it. You know, you can just, you drill a bit and you take it up, or you just take some sand and you take it up. There's a lot that can be done quite easily. So it's very, very interesting and very, very useful part of experiments. So how do you select those experiments? A lot of missions, you, as an analog astronaut, so when you apply, you actually are asked, do you want to propose an experiment? Or you can also, as a scientist, just send an experiment and the mission will review it and see, does it fit in the overall thing? How complicated is it? And what's the scope? Who is the PI? And are you available during the mission? The problem is, as the PI or the PI needs to be available for contact, because the analog astronauts might not know how to do everything, the ground support might not know how to do everything, and the PI is obviously the person who's the most, you know, best placed to actually make the final decision if there were to be something out of usual and you need to change and you need to take a quick decision. So they need to be absolutely available. Then you need to see, okay, is my experiment taking 3 times more than the average experiment? If one experiment takes 2 hours, my experiment takes 68 hours, it means that I could fit 3 other experiments doing my experiment. So is it really worth it? Obviously you could argue that if you were to have 3 experiments and you were to take a bit extra time on each of them, in the end, you wouldn't be able to perform all of them because it would be overlapping on the flight plan. It wouldn't be as correct. So you could argue that it's not always a good thing to have 3 experiments compared to just 1 from a flight plan standpoint, but also from a training and protocol for the analog astronauts and ground support center. However, if you were to look into just prestige and possibly money and outreach, having more experiments for analog missions means that they have more collaboration with the outside world, like different universities and different companies. And that means possibly more money comes in and more sponsorship, and that actually helps in the viability of the mission. Also, it's more interesting for the astronauts. So they have only 2 experiments of 10 hours. It's not as fun as if you have 4 or 5 different experiments, because if you don't like one, possibly you like 1 or 2 others. So there's lots of things that you have to take into account. Really, is what's the scope? If the scope is like, can I scratch my toenail with my other foot? That's not interesting. Obviously, you need to find something. Why is the analog environment interesting for this? What would it bring? How many hours does it take? Etc. etc. So these are basically ways you can think of when you apply to do an experiment. Think about what's the scope? How long would it take? What are logistics involved? How many people will be in there? What's the preparation? What will be training? Am I available as a PI? And am I going to publish something, for example? And think about the training for an astronaut. So for almost every experiment, you're going to create a protocol. Why? Because it's easier for the astronauts. Astronauts have sometimes 10, 15 different experiments to do. And often, you have to remember, they're not necessarily trained in the same field as you are. So you could be a biologist, and a chemist or physicist or geologist. And it doesn't mean that you don't have any lab training, it just means you're not going to be attentive to the same things. Material scientists, for example, we don't behave the same way as a civil engineer, because we don't work with the same particles, we don't work with the same materials, we're not attentive. And that means that if one person does an experiment and the other does, the results might be actually different, because we haven't done the same extra cleaning steps, or we haven't been that precise, because we don't realize how important it is. If you put everything in a protocol, regardless of your training, if the person is following it diligently, it should be fine. It should be fine. So the protocol is there to help the astronauts, but it's also to help the well-being and the yield of the experiments. Then the other thing is, if you have a protocol, the mission control center, the ground support, can really be like, oh yeah, it's written here, this. They can follow at the same time what the astronaut is doing. If there's no protocol, the astronaut is just doing peef, paf, poof, and then maybe it explodes, maybe it works, but the ground support doesn't know, or they would have to look at the camera, or they would have to ask questions every 2 minutes. Whereas if you have a problem, you say, well, okay, protocol, point 2A, point C, or whatever it is. I didn't manage to do it. I put 122 milliliters instead of 120, and this happened. And then you can go back. So this is, the protocol is absolutely crucial, really. Even if you were to do something very, very easy and dumb, just having those protocols helps everyone. Helps the PI, helps the analog astronaut, helps them ground support. So create a protocol, make the astronaut read it, then ask them, is everything clear? That's the thing, you could create a protocol that is absolutely messy and they have no idea what's going on, they don't understand anything, and that's just not working. So this is where you do also laboratory training, if relevant. Obviously, some experiments don't need any laboratory training, but some do. So in laboratory training, for example, you would show how do you perform the experiment, what are some of the points where you have to be attentive. Some of the experiments are very straightforward, but again, some people never done laboratory work. Some people have not the right training for it, and therefore they could possibly do some very, very stupid mistake you would never think of because you are well trained, but they're not. And you can't expect them to know everything. And this is where the training is basically a safeguard. It tells you, well, actually now everybody's up to the same standards. Everybody knows how to do it. Everybody can be fine with it. So yeah, here on the left, you can see that we're training for the red mass experiment where we're extracting the perchlorate. So we were shown basically in the laboratory at EPFL in Lausanne how to perform the experiment. And on the right hand side, we were trained to use geophysics measurements. So we had the PI coming and showing us how to perform the experiment, how to use the machine, and we did the whole experiment so that when the analog astronauts would perform it later, they would be trained. And also everybody was trained on it, which meant if one of the analog astronauts was sick, one of the ones who was supposed to perform it, then there was a backup who already knew how to perform it, or at least knew to some extent, and then they could just read the protocols and be briefed in and it'd be fine. So that's also the thing, is I don't train only one astronaut on this, train as many as you can within the time that you can, just to make sure that there's always somebody who's received the right training. And obviously contact with the PI. If you have any questions, obviously usually you would ask first ground support, but if you already know what the PI really wants, it makes it way easier for you to perform the experiment. If they say, well, we're doing this measurement, but what we really, really want is that it's super high quality on this point, or that you really spend time, and if you see that, for example, there's too many vibration or there's too many people, then it won't work, then you're already more attentive. You're like, well, actually, we did an experiment, but we're not careful about this. And that really helps. If you know what a person wants, what they expect of you, then you know what your work is, going to be, what's the quality you should expect, and why you're doing it also simply. If you just feel like a puppet and you're being told to do A, B, C, D and shut up, it's okay, it's your job, but the fact is it's better if you know why and how you're doing it and what is it going to bring to the next person. So that's quite important, really, just to know, okay, the PI is expecting this for me, and this for their bachelor thesis, the master thesis, the PhD, or the publication, or just some very important result to confirm an experiment, then it really makes you feel, well, okay, what I do is important, it really needs high quality. So an example of what we call standard operating procedures template, just so you know, an SOP, so standard operating procedure, that can be used for anything. So it's not just for experiment, it can be used for communication, it can be used for, I don't know, eating, cleaning, whatever it is. So even when going to sleep, you can use an SOP. But you would use one for experiments, for example. So you put like your mission logo, what work package. So for example, there we put science. for example. So work package would be, for example, your logistics package, your astronaut package, your science package, whatever the way you define your mission. And then you put the SOP number, you put what date, and how has it been reviewed. Why did I say reviewed? Because obviously sometimes your procedure will be updated. For example, when the astronaut read it the first time and they say, well, this is bad, I don't understand anything, can you please revise it? And that's when you revise it, and then you find, oh, that's fine. Or then the PI said, actually, could we do that extra measurement, because when we did the training it only took 4 hours instead of 5, so we have 1 hour, we want to put this thing extra. So you put the revise so we know exactly what's going on. Then you put the purpose. So what's that standard operating procedure, for example? What's the scope of it? For example, you put experiment A, B, C, D on this. Prerequisites, do you need any other papers with it? Do you need any training with it? Responsibilities, who's responsible for that? Then you go through the whole procedure. So this is where you would say, take glass A and glass B, put them together, then after 60 minutes of wait, put whatever it is. That's where you put the whole thing, put any references that the astronaut might need to use, and also put the key parameters tested. So if the astronauts, again, can't remember exactly what's the scope, they can go back, look at the key parameters, and like, actually that was ABCD that we were trying to test. So yeah, so this is just an overview. Obviously you do the template the way you want it, but it's just to help you. Now, what are the logistics involved in the experiment? You would think it's quite easy. You just say, I need A, B, C, D, and that's fine. Actually, the main problem is if you were to do a lab experiment, you don't have the lab environment, okay? So you don't necessarily have a controlled temperature, pressure, and humidity. So you have to think about that first. You have to think, okay, is this going to impact my experiment? Is it planned? Is it what the PI wants? Do they want it to be impacted by the fact that we don't have a controlled environment? Or is it mostly that the fact that it's performed by non-necessarily 100% trained personnel? They train to do it for the mission, but they're not biologists or chemists or whatever it is that you actually need. And you have to think about all the equipment that you need. So, for example, an experiment in geology or chemistry can easily need, I don't know, 20 glasses or 20 small magnets, whatever it is. Sometimes something as dumb as a magnet can ruin your experiment if you don't have it. So you really have to be thorough. You have to try to have double of everything in case you break something, in case you forget it. The problem is that also increases the cost and increases the storage space. So you really have to find a compromise. One example of an inventory problem we had, so one of the experiments we had to filtrate, and during the rehearsal, during the training in the lab, we had a pump. So basically you put your sand and you put your paper, well, your liquid sand, and then you have suction going on through the pump. The problem is, during the mission, we didn't have a pump. And that actually completely changed the time we needed for the filtration process. So much so that we had to use 4 or 5 more hours to actually perform the whole experiment. So that was a big problem, because it was tested one way, and then in the inventory we didn't have the same equipment. Maybe it was too expensive, maybe we can get it lent. But basically it changed the parameters, it changed the whole thing, and it changed completely our flight plan. We had to be extremely flexible. We had to be like, oh wow, do we abort the experiment? Do we continue and then we cancel another one? Can anyone else do our experiment, etc., etc. So we had to find a way. It worked in the end, but it was quite interesting because it was really just a small difference. And then we were missing a cable, so we had to find another cable. We had to make a makeshift magnet. Lots and lots of things that seem really not that important when you're on Earth, but actually when you're in space, when you're isolating, when you can't get these things easily, makes a whole difference. Your whole experiment could be completely ruined if you haven't checked your inventory. So you really have to be thorough about what you want. You have to think, I'm not in a normal environment, that might actually affect. I'm not with normal trained lab personnel, so that's going to affect things. Maybe they'll be a bit more clumsy, or maybe they'll be a bit more slow, etc., etc. So you have to really have kind of a safety factor in it and think, well, I need a bit more of the equipment than normally necessary. So yes, you really think about those differences and see how it impacts things. And yeah, for the flight plan, always account more time. Sometimes the experiment takes less time, But usually the first day, especially when the astronauts just landed in the base and they're still getting to know each other and things around where's what, just finding the equipment, even though they are the ones who placed it there and you put the number and blah blah, you still take way more time than you would think. It's incredible, but even a small base, you're like, where's this, where's that? And then if one of the astronauts just misplaced it because they used it for something else, then I don't know, suddenly the sieve for the experiment is in the kitchen, and then you have to go all the other way, and it takes way more time, and a 1 hour experiment suddenly takes 2 hours. And it doesn't seem to be a big deal, but when your flight plan is planned from 6 in the morning to 10 p.m. without break, then you have a problem. You have a problem. Or the only break you have is for lunch, and then suddenly you can't eat lunch because you're supposed to do the experiment. That's a no-go. The health of the astronaut is actually a priority. You can't just put the experiment on top of that. So that's a big problem. And another huge problem, one that you would never think of, is the ethical requirements. So any experiments that you might do that is biology or medical focused has an ethical requirement, and ethical committee can be really, really tough. It's good. Obviously it's good. You don't want anyone to be in any sort of danger, any sort of trauma, any sort of damage. Obviously it's great. However, it can make it very, very tedious. So if you do have an experiment that involves ethical parameters, to do submit them as quickly as you can. Sometimes also, if you work with a university, the university has an ethical committee, then maybe your location or your country has also an ethical requirement, and then if you're with a company, maybe there's a third one, and then you have to get 3 of them approved, not just 1, but 3, and that's actually really, really tedious, and it's more time that you want to spend on an experiment. And then obviously PI2 MCC, 2 astronaut contact, always make sure that they are available to talk to the astronauts and make sure that you have the right information. Once you have your experiments results, so one thing that is done, for example, is if you have people who got a bachelor, master's thesis or PhD thesis, and they ask the astronaut to perform those experiments, then they will use them in their bachelor, master's, and PhD publication, or just a thesis in general. So it's quite interesting. Obviously, this is something that happens quite often, that you use them for students' research, but some publications also existing are in the International Astronautical Congress. So for example, this year was in Paris, next year is in Baku. You could see quite a lot of Analogue space mission work that was actually published, and there's all the conferences where you can publish your results either with a poster or an article, presentation, whatever it is. There's quite a bit of research in Analogue space mission that has been accepted, as long as you have usually good quality results and you try to perform it as well as you could, then normally it's not a problem. So yes, this is the kind of things that you can do. Obviously I can't guide you on how and what to do, that depends on the experiments, depends on your field, but just so you know, you can publish your results if you have performed an experiment and it's obviously of a high quality standard and you have enough. Just to give you an example of publication, so these are 3 examples from high seas in Hawaii that we just mentioned in the beginning. They have a lot of publications, and you can see some of them is at the ISC, International Astronautical Congress, well actually 2 of them, one in Toronto and one in China, and then there's Human Space Symposium in Cologne, so you can see there's like different places where they can publish things. For example, the first one, monitoring cephalad phase shift induced nasal tissue swelling in 70 days, 6 degrees head down tilt. That is a very much medical publication, very, very precise. So you can see that they did high performance research. And then others is high seas, long duration human spaceflight analog in Hawaii. This is a bit more of a like general publication. Then the third one, demonstration test of electrical lighting system for plant growth in high seas and Mars habitat, more biology like agriculture oriented experiments. That's also quite interesting. So you can see there's quite a wide array of things that you can publish, quite general, quite large, up to you really. But it's quite interesting. So don't hesitate to publish if you believe that, try to publish if you believe that you have the necessary results. Obviously do try to have high quality standards, but analog missions are coming really into force in the world of science, and it's quite interesting to see how it's taking a broader aspect now. Okay, so this was for today, experiments. Hope you're having a good time still, and have a great day.